All right, our next speaker will be Mark Simkin from Flashbots.
Okay, hello everyone. I'm going to tell you on some work in progress at Flashbots on building fast anonymous communication systems, which currently have the name FlashNets. Okay, so what is a, oh, I can guess, see it here. What is an anonymous broadcast system in the first place? So the one that we kind of consider here is you have, let's say, 3 parties. Each of the parties has a message. And these parties would kind of like would like to broadcast their messages to the network, but they would like to do so anonymously, so each message should not be linked to the sender of the message. And how this usually works is that the parties will in some way communicate with each other, and at the end the network learns the 3 messages, but cannot see that like M1 was sent by party P1. It could equally likely be sent by P2 or P3. Okay. So this is like a field that has lots and lots of research over many, many different years. So now let's draw some triangles. Kind of like we can look at like some very general approaches and we can put them in this triangle. So we have kind of like 3 properties that we might want to have, which is we would like to have our solution to have low bandwidth requirements. So the parties should not send around too many messages before the messages get revealed. We would like strong anonymity and we would like low latency. So the round complexity of the protocol should be small. And if we put something like onion routing as a blueprint, then it's great because it has very low bandwidth requirements, but it provides usually not very strong anonymity guarantees. And also the latency is not great. So you can trade off some of the parameters, but that's very roughly where it falls into. You can also look at mixed nets. Mixed nets provide very strong anonymity, but they are very bandwidth intense and they have many rounds, so they're also not very good in terms of latency requirements. And what we do kind of like in our current work is we trade off basically to have kind of okay bandwidth, but in exchange we get strong anonymity and very low latency. So this is kind of what we optimize for. So we optimize for 2 of the parameters and we pay some price in the 3rd parameter. Okay, so now let me explain you on a very high level how. Okay, so now that we kind of like outlined roughly what we want to do and also how it roughly kind of like compares in efficiency metrics to existing other approaches, let's see what the high level ideas are behind our system. So on a very high level, what we will do is we will have kind of like 3 groups of parties on the network. We will have the clients which have the messages that they would like to broadcast. We will have some aggregators and we will have some servers. And in terms of trust assumptions, what we will have is that these aggregators are fully untrusted, that they can all be malicious. This will not affect anonymity. And we will have some threshold honesty maliciousness assumption on the servers, meaning that some of the servers might be malicious, some of them might be honest, and depending on how the construction will be parameterized, we can tolerate different trade-offs between liveness and privacy. So kind of if you want to have as a maximum amount of privacy, then you can set the parameters so that even if all but 2 of the servers are corrupt, you still have privacy, but then liveness will suffer, and the other way around, you can kind of maximize for liveness, but then you need to reduce your privacy threshold. And the important thing that we will be doing, and for those who are familiar with ZipNet, is it will follow kind of like the line of what ZipNet does is we will be using TEs on the client side, and we will be using TEs on the server side. But importantly, we will be using them for liveness, not for anonymity. So what this means is that if TEs were to break, then the protocol will noticeably start failing because messages will not be delivered anymore. But TEs breaking will not affect anonymity of the messages. So the anonymity is a classical non-collusion assumption on the servers that says at least some servers are honest. Okay. So the starting point is a basic building block from secure computation called secure addition. And let's assume we have 3 clients. They have 3 messages. And let's assume that just one of these messages is not 0. Okay, so in this case, we have these 3 messages. The first message is non-zero, and M2 and M3 are just 0. And what they can do is they can basically say, well, I take my message locally, M1, and I split it into 3 values such that the sum of those 3 values is my message M1. Okay, this is what is called an additive secret sharing, but you could also make it a threshold secret sharing if you prefer this. And in this case, kind of like the important takeaway is that like now that I split M1 into these 3 pieces, unless you have all 3 pieces, you will not know what M1 is. And now what they will do is each party will send their first share to server 1, to their second share to server 2, and the third share to server 3. These servers can sum them up locally. And if I compute the sum of those revealed values, then I get kind of the sum of the 3 messages. But because only one of them is non-zero, I just get my first message. Okay, so like this is some kind of like splitting stuff into sums and then summing them in the right order. And what this guarantees you is that now the message that was non-zero was revealed, but the servers cannot see which client sent the message and which client sent the 0 message. And even if some of the clients are corrupt, they cannot see that either. Okay, so based on this very simple, very old building block, you can now build an anonymous broadcast system. So now what we do is, in the simple example, we said one party has a message and the other parties have zeros. So now we just assume we have a bunch of separate communication slots, and each party assigns their message to a random communication slot. So here they are kind of like viewed as an array. Now the first party says, I will broadcast my message on the second communication slot. And the other parties might pick some other slots. They do it independently, like completely at random. And now what we do is we basically do the same thing that we did for one slot. We now just do in parallel for all the slots at the same time. And because the message locations are completely random, we have anonymity because kind of like the location where the message appears is independent of who the original sender was. But this approach runs into one problem, and that is, well, each party independently randomly assigns their message to a slot. Maybe some parties will pick the same slot, in which case we kind of like, we have a collision. We don't really have one party having a message and everybody else having a 0. Okay, so now if we look at this and what we kind of like did with this addition, well, we really just added 3 vectors to get this vector at the bottom. And if we say we have a collision, then we effectively, in the bottom vector, somewhere we have kind of like added 2 messages together rather than just independently sending the messages. And what we now can do is we just do a trick. Well, we do it twice. So we kind of like run the protocol twice effectively with different random choices. Now, in both of those, I might have collisions. But the nice thing is, well, if I look at these 2 arrays, then in this one, M2 did not result in a collision, so I can extract M2. And now if you assume that based on knowing what the message is, I can determine the location, maybe it's like a hash function of the message determines the location where the message is placed in these arrays, well, then I know that I can just remove it from the corresponding location in the second array. At this point, I had a collision in the bottom array, but now I resolved it by just deleting the message from the sum. And now it turns out that I can remove the other 2 messages from the bottom array. And in total, I extract all the messages that I want to send originally. And this is kind of like a simplified view of a more general data structure, which is called a stacked invertible Bloom filter. And in this example, I showed the 2 arrays being of the same size, but actually you can pick one to be somewhat proportional to the number of messages, and then each subsequent array to be like of half the size of the original one. So you get like a cascading smaller and smaller arrays, and you effectively kind of like get less than a factor 2 overhead in the number of slots that you need to send around, compared to just like assigning party I to slot I, which is like the minimum amount of communication you would need to do in this approach. Okay, so using this approach, now what happens is the parties basically share their messages, then the servers kind of like collect the messages that are intended for them, roughly speaking, and then they output kind of these like sum values which reveal the messages. Now, if we look on the left, that's a lot of messages. In particular, if we have a lot of servers, then kind of like the number of messages increases because each client sends 1 message per server. So one thing that we might want to do is we want to reduce the overhead, or like the bandwidth overhead, at least on the server side. And this is where the aggregators come into play. So now we have these aggregators, which are completely untrusted parties. And all they do is they take some of those messages and they just add them together on behalf of the servers. And after they have done this, they just forward that to the servers, and the servers then do some sort of decryption. I'm being fuzzy on how the decryption works and stuff, but like just trust me that it like works roughly like that. So the aggregators take a lot of messages, compress them into one small message for each server, and forward them to the servers who now just need to do basically a decryption operation. Zooming in a little bit on this approach, and I forgot what comes next. Okay, so yeah, so this is authenticated by the clients. So they authenticate the messages that they send. But after the aggregators maul with the messages, they add them together. The resulting messages are not authenticated towards the service anymore. So this is a problem because now the aggregators can basically perform a denial of service attack on the servers because the server has no way of distinguishing good from bad messages. Zooming in a little bit more, if we look at just one aggregator, then effectively what we have is we have a bunch of authenticated messages under different keys. And what the aggregator would like to do is would like to compute the sum of the messages and get some kind of authentication tag for the sum of the messages. And what we kind of like show that I won't have time to get into detail here is that you can do this very efficiently by relying on some concepts of homomorphic hashing, which gives you exactly this kind of authentication tag with like good concrete performance. Yes, I don't know how fast I was, but I think fast. Oh, okay, yeah. So thank you. And if you have questions, then we have a lot of time for questions.
Thanks, Mark, for the great talk. Maybe I missed the part regarding T's, but what role do T's play in your protocol?
Right. So the role of the T is that I said, now I take every message and I put it into a one random slot. If I wasn't running this in a T, a malicious adversary could block the whole system by just like filling up all the slots with garbage. So the T ensures that you really just put it into one slot and the protocol remains live because at the end you can do the reconstruction of the messages.
What's the application or use case that Flashbots is thinking of for FlashNet?
So there are several different applications. One of them is for private block building. So you can do this twice. You can kind of once bid for building the block. And then in the second round, if you won the bid, then you can kind of like publish your block without revealing who you are.
Mark, you're from the like academic cryptography community, and in doing this project, I know that you've been tailoring it to actually being useful in practice. I'm curious what that experience has been like. I think it might just be interesting to hear for the more academic crypto people in the audience.
So public key operations are already like often a no-go in low latency situations. And as it turns out that AES and I calls are not an infinitely free resource. So there is a point in time where this is too inefficient, even if you just do AES calls. So like you really need to optimize for both symmetric operations and public key operations. I think that's one. But it always depends on the settings. So like here we really focus on the lowest latency type of application. So we want really the protocol to produce messages fast. And then these kind of things become an important issue.